In this video, we're going to work on extending the concepts of limits and continuity to functions of two or three variables. And let's just do a quick recap about the concept of a limit when you have a function of this form. So let's say you have a function y equals f of x. So this function has one independent variable, one dependent variable. And when we are trying to look at a problem, let's say the limit as x approaches x0 of this function, remember what this operation is saying. It's asking you when x gets closer and closer to x0, what happens to your function f of x, right? Now, what do we mean by closer and closer, right? Again, we're not doing this in a very super precise way, but think about it. We use our number line to represent, the x values. So we have our x0 somewhere on the x-axis. And because our x-axis is linear, when we talk about approaching x0, well, there are only two ways that we can approach x0, meaning we can approach x0 from the right this way. So like if our values of x are a little bit bigger than x0, but they're getting smaller, or we could approach x0 in this direction and say, well, our values of x are smaller than x0, but they are getting bigger. And then that gives rise to these one-sided limits. So we say, well, what happens? So like in this direction, if we want to specify that we're approaching x0 from the right, then we would do that, right? And say, okay, well, what's the limit of our function when x gets closer and closer to x0 in this direction? And similarly, if we specify this direction from the left, then that's where we come up with this notation. And then we say, well, if these two one-sided limits are the same, then that is defined as the two-sided limit as x approaches x0, right? So basically we say that so the limit, and this is just a quick restatement of that theorem from previous work, this limit is equal to L if and only if the limit from the left is equal to the limit from the right, and they're both equal to L. Right, so that's kind of just a quick summary. It doesn't. I'm not going to really go back through all the little tricks from algebra that you can do to evaluate limits, right? And there are quite a few of them. But this is really the concept behind the limit of a function of one variable. So then the question is, how can we extend this concept to a function of several variables? Right, and let's just go up one notch, right? Let's say we have a function of two variables. All right, so let's do this. All right, so let's scroll down just a little bit, and so let's say z be a function of x, y. Right? So now we have a function of two variables. Well, let's think about what would represent the domain of a function of two variables. Again, when you have a function of one variable, a line, an axis like this is sufficient to represent the domain. But when you have a function of two variables, well, you need something that's two-dimensional. And we do have that. We have our xy plane. So let's say we have our xy plane, and now I'm going to pick an ordered pair, let's say x0, comma y0, like that. right? So there's our ordered pair. So let's see. So suppose our arbitrary ordered pair xy is allowed. So like think of it as, like, is that like what you're seeing on my screen? My little pointer. It every time I move it, it has a different value of x and y, so I can move it around. What if I begin to move it in such a way that I'm getting closer and closer to this fixed point? I never quite get there, right? But I'm getting closer and closer to it. Then I might ask, what happens to my z values, right? As the ordered pair xy approaches this fixed point, x0, y0. Now, the interesting thing, look at my little, marker here. It seems like I can get closer and closer to x0, y0 in lots of different directions. In fact, let me actually draw some of these directions. So for instance, I can certainly use the same directions here that we're used to, going from the left, that's one direction, going from the right, that's another direction. But why not come from the north? Why not just we could go this way as well. There's another direction. Why not come in from the south like that? So right away, we have four. And again, these are all really simple like lines, but what about something more curvy? What if I did this and say, okay, along this curve, again, I'm making whatever direction or however straight or curvy my path is, I'm going to make sure that they're all heading towards that same single point x0, y0, right? And then you can have some really fancy ones. And notice there are actually infinitely many directions from which x0, y0 can be approached. So just thinking about that, you see a pretty stark difference between a function of one variable and a limit, right, versus a function of two variable and its limit, right? So I'll just make a note here. So there are infinitely many. So there are infinitely many paths or directions. I'll use paths, so infinitely many paths along which xy can approach that fixed point, right? Can still approach my x0, y0, right? But again, the concept is still the same. I'm getting closer and closer to a fixed point. What is happening to my dependent variable, right? So what we can do, however, is now utilize our concept of those curves. Remember how we defined curves as vector functions? And of course, some could be linear. We looked at lines. And then some are curvilinear. We looked at the nonlinear function. So what we can do is this. So we're going to define what it means, right, to approach a point along a curve, right, and then use that concept to explore the idea of a limit of one of these functions. So, and what I'll do is I'll state the result for if you have a function of two variables and also a function of three variables. So let's say this. So if C is a smooth parametric curve in 2 or 3 space, given by, and we know what those parametric equations look like. That's where you have a single equation for each variable. So in 2 space, you would have like x equals some function of t, and y would be equal to some function of t as well, right? So this is what it would look like in 2 space. In 3 space, same thing, just a third equation for z. So it looks like this, and then z equals z of t. All right. So again, these are the parametric equations. If we wanted to, we could write it in vector form. The specific form isn't that important, but it's the idea of, okay, having these curves. Now suppose we have, and again, notice that we're using the word smooth here, and we have a very precise definition for what it means for a curve to be smooth. Well, if this smooth curve produces the point here, either in 2 space or 3 space, by a certain value of t, right? So if we have this, and if your point, for instance, x0 corresponds to evaluating my x equation at a specific point like this, and then I'll just go ahead and state it for all for the 3 variable case. So it looks like this, right? And z0 equals z of t0. So in other words, if you know the value of t that forces your curve to produce this point, right, the smooth curve, right, then the limits. So let's look at the limit notation now for these. So we still use LIM. And now in the 2 variable case, we're going to have our x comma y approaching x0, y0, right? So down here, instead of having just x approaching x0, we have our ordered pair xy approaching x0, y0. And then we still put our function here like this. So this is our function of 2 variables. And then, so what does it look like for 3 variables? Well, it gets a little kind of cumbersome at the bottom here, but you have an ordered triple, x, y, z approaching x0, y0, z0, and then your function goes here, right, like that. How do we define these? So these limits are defined. So are defined by, so if we are, again, if we're going to approach them along a specific curve, this curve that's given parametrically, then the limit as, let's get this, so x, y approaches x0, y0, and if I say along, put a little bit more information now, so there's lots of stuff going on under your limit notation, but along this curve C, right, so f of x, y, so how do we define this? What we say is we're going to essentially express the limit parametrically. So we're going to express the limit in terms of t. So the curve is defined in terms of t. We're going to try to express this limit in terms of t. And this is what it looks like when we have a function of 2 variables. So literally, xy approaching x0, y0 is replaced by letting the parameter t approach t0. And this is helpful because it reduces the complexity of this limit. It breaks it down. Instead of having multiple variables, it breaks it back down to a limit that involves just one variable t, right? And t is going to approach the value t0, right? And then what do? Well, we replace x with the x equation, so x of t, and then we're going to replace y with the y equation, y of t. So it looks like this. So f of x of t and y of t. So this is how it's defined. And then what we're able to do is then use our techniques from Calc 1 on this, right? Because the only difference between this limit is we're using the letter t as opposed to the letter x, right? So that's what it looks like for a function of 2 variables, and for a function of 3 variables, then it's the limit of x comma y comma z approaching x0, y0, z0, and then here's our function f of x comma y comma z. Again, all of this, right? Because we have our nice smooth curve that is approaching x0, y0, z0 as t gets closer and closer to t0, then it looks like this. And then simply replace x with the x of t equation, replace y with the y of t, and then z, this is a z, with z of t. Right. Let me specify. This is along this is along one of those paths that I drew in blue earlier. Right. So that's the definition. So it certainly looks like a mess. But let's jump right into an example to see how this plays out. Right. So we're gonna. And let's use a function like this. So let f of xy be equal to, let's say it's negative xy over x squared plus y squared, right? And what we're going to do is find the limit of f of xy as xy approaches, let's approach the origin, but then we're going to specify these different paths, right? Along, and then we'll just go through the different parts. So let me scroll down here. Let's do part A. And part A, so here our ordered pair is going to approach the origin, and it's going to do so along the x-axis, right? So it's along the x-axis. So let me do this, right? So here's our 0, 0. So our path here, and I'll draw this in blue, it's either that way or that way, right? So we're stuck on the x-axis and we're getting closer and closer to the origin. So what we have to try to do is to express this path parametrically, right? But let's think about it. If you are along the x-axis, x can be any real number, right? But y has to be 0. So here is the parametric form of this path. So this implies, right, x can be, and that any real number, that's what we're going to use as our parameter. So x can be any real number, right? And then y would have to be equal to 0. So here are the two equations that we're going to work with. So our x of t is equal to t, and our y of t is equal to 0, right? So two simple equations to work with. And then the thing to note is, as x approaches 0, then it means t approaches 0, right? So let's set up this limit. So first, let me write it like this. So the limit as xy approaches 0, 0. Here is our function. And I just want to point out, if you notice, if we try our old familiar trick of plugging in your x and y, right? If you plug in 0 for x and 0 for y, you get that familiar 0 over 0 form, right? Which still means the same thing. It's indeterminate. It's just that here, algebra doesn't quite work for this one, right? But we'll see ones where algebra will work. Okay, so let's express this entire limit in terms of t, right? So again, as xy approaches 0, 0, that is equivalent to saying that t approaches 0, right? In fact, let me specify and say this is along the x-axis. So along the x-axis, I can simplify this limit and say this is the limit as t approaches 0. And then what I can do is replace all the x's with t and all the y's with 0. So this is what I have. I have negative, and then I have t times 0 over, then I have t squared plus 0 squared. But simplifying this, right? So we have the limit as t approaches 0 of negative. I have 0 in the numerator and t squared in the denominator, right? And as t might be getting closer and closer to 0, but it's not equal to 0. So here, this expression simplifies. I have 0 in the top, and I have something that's small and, positive in the bottom. So this entire fraction simplifies to 0. Another way to say it is, okay, if I just look at this expression and simplify, right? And this is going to reduce to 0 because my denominator is not 0. So this ends up being, let me write one more thing. Do this, that's 0. And then the limit of that constant is 0, right? So what does this mean? So this particular function, as xy approaches the origin, but specifically along the x-axis, this function gets closer and closer to 0, all right? Okay, so let's try a different path. Let's do part B here. Let's try a different path. And I'm going to make it linear, but instead of it being horizontal, I'm going to have it have a slope of 1. So let's say we're going to approach the origin along this line, y equals x, right? So let's just do a little sketch of this. Right, so again, we're approaching the origin. And I'm intentionally drawing the blue, these paths that we're taking, I'm intentionally drawing them where they don't actually touch the origin. So we're getting closer and closer there or there. So that's the line y equals x. And we're getting closer and closer to the origin. Let's express this line parametrically. And we do the same thing. We could just let x equals t, which then means y would be equal to t. That's because x and y are equal, right? So again, if we let t be this, then y would be this. So here are our x and y equations. So x of t is t, and y of t is also t. So now let's again start with our original limit, but now we're going to specify what it's like or what's going to happen when we approach the origin along this line. So we have the limit as x comma y approaches the origin now along this specific path, y equals x, and our function is the same. It's that negative xy over x squared plus y squared. So now let's express this entire limit in terms of t. So in order to approach the origin, right, t would have to approach 0. That would force x to get closer and closer to 0 and y to get closer and closer to 0. So in this case, t would have to approach 0. And then we again, take the x equation, which in this case is t, and replace all the x's. So I'll have negative t, and then do the same thing for the y. So replace all the x's and y's with t's. That's because of this parametric form. So we have t times t, and then over, and then I have t squared plus another t squared. And let's simplify this, right? Notice, if I plug t equals 0 in here, I still have 0 over 0, which doesn't mean anything. But let's use some algebra and simplify this. So what do I have? I have the limit as t approaches 0 of negative t squared over, and then at the bottom I have 2t squared. But now I have a common factor of t squared, so I can get rid of that factor that's giving me the 0 over 0. And what am I left with? I'm left with another constant, and that constant in this case is negative 1/2. So the limit, right, of this function as we approach 0, 0, if we take a different path now, so if we don't move along the x-axis, instead if we move along the line y equals x, it turns out that our function gets closer and closer to negative 1/2, right? All right, so what does this all mean? Well, it means this is similar. This is similar to the process of those one-sided limits. And remember what happened, I should say, previously in your first course in calculus is when those one-sided limits were different, we said that the overall limit does not exist. And the same thing is true here. If we are able to find two different paths, right, that take us to our same, or take us closer and closer to the same point, in this case the origin, if those two paths produce two different values, so along the x-axis our function approaches 0, along the line y equals x, again as x approaches as xy approaches the origin, here the function approaches negative 1/2. And because these two numbers are different, we say that the limit does not exist, right? So let's state this. So since, let's write down our function f of xy is equal to negative xy over x squared plus y squared. Since this function approaches two different values, I'm not going to call them a limit or call them limits because they're not limits, right? Just that they approach two different values, right, along different paths approaching 0, 0, we were in both cases, both A and B, we were getting closer and closer to the origin. So since we produced two different values by taking two different paths, we can say that this limit of this function, I'll just say f of xy, does not exist, right? So does not exist. And that's the general approach. Now you might say, well, how do I know what to use, right? Well, that's kind of where, experience comes in. And at this level, without going super, super deep into it, you would be given the paths, right? You'll be given the paths to say, okay, along the x-axis or along the y-axis or along the line y equals x or some other path that is guaranteed to go approach the point, and then you would go through your limit calculation. And if you can show that two different paths produce two different values, then you'd say that the limit doesn't exist. Now, let's say we did A and B. and they were both the same, we can't say that the limit exists because we've only checked two paths. In theory, we would have to check infinitely many paths for this to work, right? So let's kind of summarize this in the form of a theorem, right? Always good for a theorem. So there are two parts to it. So if our function, I'll just use this limit, or this notation, sorry. If our function approaches L as xy approaches x0, y0, then f of xy will approach L as xy approaches x0, y0 along any smooth curve. So along any smooth curve, right? So what this is saying, if you know that the limit exists, right? So if you know that the function approaches a fixed value, right, then no matter what path you take, right, the function is going to get closer and closer to that number, right? The other part of the theorem says this: if the limit as xy approaches x0, y0 of f of xy either fails to exist, right, or f of xy approaches different values, right? So our f of xy approaches different values let's see, along two different curves like we saw earlier, then the limit of our function as xy approaches x0, comma, like that, of f of xy, then this limit does not exist, right? So does not exist. And let me specify here, if this limit fails to exist along any c, so I'll just say along any c, right? So if you pick a path and somehow the limit works out to be, let's say, like you end up getting like 2 over 0, then if it doesn't exist along that path, then the overall limit does not exist. And the other possibility is if your function approaches different values along two different curves, as we saw earlier in that example, again, then the limit does not exist, right? So sometimes this is referred to, this part B is referred to as like the two path tests. Like if you can find two paths that produces two different values, right? The function approaches two different values, then you can conclude that the limit does not exist. All right, so what we're going to do is, so as this video doesn't extend for too long, we're going to stop now. We're going to continue, do a couple more examples with the limit, right? And some will be more familiar than others. And then we're going to tie it all in with the concept of continuity. So if you want to see how this story ends, hop on over to the next video. See you then.